Hey folks, in this video we're going to look at the math side of absolute dating, or radioactive dating, or radiometric dating. All those names apply. This process will be a type of exponential decay. You might be familiar with this from your math class. The idea with the exponential decay is that in some period of time, you can define a period of time. In that period of time, there will be a consistent percentage of change over time. Not a consistent number, but a consistent percentage. So as an example, when we flipped coins in class, we started with all our coins head side up. We flipped the coins, and then the ones that came head side up, we flipped them again. We expect that as we go through that, we're not always going to flip the same number of heads, but that we should get roughly 50% of all the coins that we flip coming up heads. So it doesn't matter how many we start with, we should get 50% of all the flipped coins. So that'd be an exponential decay process there. And with the coins, eventually we end up with no coins up on heads. That's where this departs a little bit from the mathematical model, because in math we would look at a function that never actually reaches zero. Now, with radioactive decay, we're not looking at coins, of course. We're looking at radioactive atoms, or radioactive isotopes. And those things, they aren't just changing whenever we flip them. They could change at any moment in time. We don't have a good way to predict when a single isotope is going to go through that process. But we can make pretty good predictions statistically on how likely they are to decay. So we have this idea that after a certain amount of time, we will have had half of our sample decay or change into a different type of atom, a more stable atom. And so that amount of time that it takes before that happens, we're going to call the half-life. And again, it's not it's not the same number of atoms each time. It's half of the number that we start with. So if we graphed this function here, we've got on the y-axis the percent of the original sample that we still have left after some number of half-lives on the x-axis. So if we start at 0 half-lives, that means that we just have 100% of our original sample. No time has passed, so this is the original moment. After 1 half-life, we're going to be down to 50%. And you might find it useful to also record fractions on it. So we're down to half of our original sample. After 2 half-lives, we aren't going to go down to 0, so it's not that the first half-life we have half of them decay, and the second half-life we have the other half. This time it's going to be half of what we had left, half of that 50%, which gets us to 25%, or 1/4. And this pattern will continue, so we'll do half of that again, half of 25%, so another half-life is going to be 12.5%, or 1/8. That's a quarter times an eighth. Sorry, a quarter times a half. Next one, 4 half-lives in. We're going to do half of what we had after 3 half-lives. That'd be 6.25%, or 1/16. And then half of that for another half-life, we'd be at 3.125%, or that'd be 1/32. And when we connect the dots here, we get this nice, smooth, exponential curve. This would be a great diagram to have handy in your notes when you're solving these problems. So I'd recommend you keep that with you. So let's try solving a few problems like this. So first one, we are making up we're rounding off the number for carbon-14, just to make this a little easier. We're saying carbon-14 has a half-life of 5,000 years. So how long will it take before only 12.5% of the original sample remains? Well, 12.5%, that probably is familiar to us. That was on our graph just a minute ago. 12.5% shows up right here. And so we had to go through 3 half-lives to get down to 12.5%, or 1/8 of the original sample. So we know that we're going to have 3 half-lives going by for this problem. So 12.5% goes with 3 half-lives. And we know that 1 half-life is 5,000 years. So then 3 half-lives would just be 3 times 5,000 years, which is 15,000 years. So after 5,000 years, we'd be down to 50%. After another 5,000 years, so 10,000 altogether, we'd be at 25%. And then another 5,000 years, we'd be down to 12.5%. Next one. Uranium-235, half-life of 700 million years. How much of the original sample will remain after 1.4 billion years? The only thing that's really tricky about this is the millions and billions here, the millions and the billions. So watch for that. 700 million is the same as 0.7 billion, or 1.4 billion is the same as 1,400 million, or maybe it's just easy to write these numbers out all the way. So 700 million, 4, 5, 6 zeros there, okay? And then 1.4 billion, 1,400 million. Okay, so 1.4 billion is 2 times 700 million. So this leads us to the idea that we have 2 half-lives have gone by. Okay, but the question wasn't how many half-lives, the question was how much of the original sample will remain. So we go back to that little chart. After 2 half-lives, we are right here at 25%. Or 1/4 if you prefer. And then let's do one last one here. Radioactive strontium decays such that 25% of the original sample still remains after 100 million years. What's the half-life of strontium? Okay, so that 25% is still there. That tells us, back to our chart, that we're dealing with this one again, 25%, so that is 2 half-lives have gone by. Oops. 2 half-lives. Okay. It also tells us that we've had 100 million years go by. So 2 half-lives have gone by and 100 million years have gone by. I can write then that 2 half-lives and 100 million years must be equivalent. So if I want the number for just 1 half-life, I'll divide both sides by 2. And I get 1 half-life is 50 million years. Oops. And there we go. That's it.